we can do some pretty cool things with these implicit plots here. This one, where is the equation of a circle. The center is at x is 1, y is 1, and the radius is 2. And we're going to use this to locate horizontal tangents on the implicit curve. So the first thing we got to do is find dy dx. So differentiate with respect to x, and you'll get 2 x minus 1 plus 2 y minus 1 y prime equals 0. Isolate y prime, so knock these 2's out, and once they go, you can bring this over on the other side, and then so you'll get y minus 1 y prime equals minus the quantity x minus 1, and then divide through, you get y prime equals x minus 1 over y minus 1. Negative sign out front. So, how do we find horizontal tangents? Well, what you do is, you know that at horizontal tangents is where the derivative dy dx equals 0. So you set whatever you get for dy dx equal to 0, and then you solve the equation. And what happens is, once we set it to 0, the bottoms just cancel. The condition for dy dx being 0 is x minus 1 must equal 0. So once you set that up, this is called, or this is what I call, the condition for horizontal tangency. It's the result of setting dy dx equal to 0. So when you set dy dx equal to 0, this is what you get. So the condition for horizontal tangency, we need to figure out, the question that we have to ask is, can this condition be satisfied back in the original equation? So another way to write this would be x equals 1. So what we would have to do is substitute this condition back into the original equation and see if we get any answers. So let x be 1. If I let x equal 1 in the original equation, then that gives me 1 minus 1 squared plus y minus 1 quantity squared equals 2 squared is 4. Alright, so that goes, and we're left with this. So it appears that we are going to get answers. Now, when we take this and solve it for y, we square root both sides. You get y minus 1 is plus minus 2, and then bring over the 1, so y equals 1 plus minus 2. So the y values that correspond with x equaling 1 in the original equation is 3 and minus 1. So supposedly we get horizontal tangents at 1, 3, and at 1, minus 1. And we could verify that because we know that the graph is a circle. And the center is at 1, 1, so the origin would be, the radius is 2. So we go, let's see. So here's a rough sketch of the equation. And we can verify our claim, right? If this is, so this is 1, the radius is, 1, 2, 3, horizontal tangent. And 1 minus, 1, 2, 3, minus 3, minus 2, no, 1, 2, that's a horizontal tangent too, so there we go. We can see that there's actually some use for this. So this is one example. This is about the easiest one I could come up with. The condition is easy, plugging it back into here is easy, and the solution is easy from there. Let's try another one and see what we got here. Let's take this curve and let's figure out where this thing has, say, vertical tangents. So you want to find dy dx, so differentiate this. You get 2x plus the product rule here. That'll be f prime g, so that's y, plus g prime f, that's x y prime, plus the derivative of this would be 9y squared dy dx equals 0. Alright, so we got two y prime terms. So to isolate it, we'll bring these two over to the other side, and that'll give us xy prime plus 9y squared y prime equals minus the quantity 2x plus y. And factor dy dx out, so that'll be y prime x plus 9y squared equals the same, and divide through. So you get y prime equals 2x plus y divided by, what was it, x plus 9y squared. 9y squared. Negative sign out front. So here we go. Okay, we were after vertical tangents. So vertical tangents is where the derivative is undefined because we have no slope. So what you do is you want to set up the condition that's going to make dy dx undefined, and that would be setting the bottom equal to 0. So the condition for vertical tangency in this case is x plus 9y squared equals 0. Another way to write the condition would be x equals 9y squared. This is the version that we're going to plug back into the original and see if it can be satisfied. So we're going to replace each x in the original with 9y squared. So to come back here, let's see what we get. Let me just rewrite this so you can see it. We get x is, oh, that's a minus 9y squared. Minus 9y squared. Minus 9y squared. So plug it in. So where there used to be x squared, that'll be 81y to the fourth. And what used to be x times y will now be minus 9y cubed, right? The x becomes a 9y squared. And then the plus 3y cubed. Plus 3y cubed equals 0. So we eliminate x to plug in, we get an equation for y. Can we solve this? Collect the like terms, so you got 81 y to the fourth. Plus 3y cubed minus 9y cubed is minus 6y cubed equals 0. And we can solve this, so you factor it out. What can come out of this? This is 9 squared, this has a 3 in it, so we'll take out a 3y squared. 3y cubed. And we'll have 27y minus 2 equals 0. And so, what we get out of this, the solutions back in the original says that in order for the condition to be satisfied, it must be the case that either y, right, both of these are 0, so either y is 0, or you set this equals 0 and you get y equals 2/27. So what we need to do is we need to get the x values that correspond with these two y values. So you have two options here. You can either plug it back into the condition, into the original equation, or you can plug it into the condition to figure out what the corresponding x's are. It's always going to be easier to plug it into the condition because the condition is generally something that's simpler. So we want the x's corresponding with these y's. So all we have to do is square it and multiply it by minus 9. So if y is 0, that gives us x is 0. So far that gives us the origin. And if y is 2/27, x equals minus 9 times 2 over 27 quantities squared. So what's that work out to? That'll give us minus 3 squared times 2 squared is 4 divided by 27 is 3 squared, so this will be 3 to the 6th. And when you reduce that, you'll get minus 4 over 3 to the 4th, which is 81. So, corresponding with y, minus 4, 81. So when y is minus 2/27, that means x has to be the value of 481. So that gives us the points 0, 0, and let's see, minus 4 over 81, comma 2 over 27. So one thing I want to point out though is 0, 0, if you notice back in the original, it makes, if x is 0 and y is 0, then it makes both top and bottom 0. Now when that happens, you really can't tell what's going on at the point that you got it at, because 0, 0 is indeterminate. So it might be horizontal, it might be vertical, it might be neither, it might be both on occasion. But I got a graph of this, and we can see what it is. There you go. The graph is a little loop right near the origin, and there's a horizontal tangent at -1/24, 1/12, and here's the vertical tangent that we found. Also, we found the one at the origin. So see, we said dy dx was kind of funny there, and that was because it's a point of self-intersection. But in this case, it does happen to be a vertical tangent, so we got verticals here and here. As an exercise, you should probably try to find where this thing has the horizontal tangent and get the condition and go through all that and see that you come up with this answer, -1/24, 1/12. I do have one more that I want to do. Because some of this stuff can get kind of tricky, I'll take this and we'll go with horizontal tangents. So just another example. So first is to find dy dx, differentiate this. So f prime g, so that's 2xy plus g prime f, and that's x squared y prime, minus the quantity f prime g, so that's y squared, and then we're in a minus sign, g prime f, so that's 2xy y prime equals 0. So collect the like terms, and that'll give me y prime. If I factor it out, that'll be y prime x squared minus 2xy minus y squared plus 2xy equals 0. So I bring these two over, and then I divide through by this, and I get y prime equals, what did that give me? Y squared minus 2xy. Alright, bring that over, divided by x squared minus 2xy. Alright, so I want horizontal tangents. So do as normal, set this equal to 0. And when you set that equal to 0, what you get is you want the top to be 0, so that gives you the condition y squared minus 2xy must be 0. And that has sort of two sub-conditions here. If you factor out the y, alright, you get y minus 2x is 0. So the conditions, there are two conditions really. If there are going to be horizontal tangents, that mean either y is 0 via this, or y equals 2x. So we go back and we see if we can satisfy these in the original. I'll take the y is 0, and when you plug that back into here, if you make y 0, what you wind up with is 0 minus 0 is 2. So that condition can't be satisfied, right? We get a false equation. When we plug this back into the original, we get 0 equals 2, which is a false equation, which means that if the condition is satisfiable, if it can be satisfied, it isn't going to come from y being 0, because there's no point on the curve where y is 0, because we set it, we plugged it back in and we got nothing. So if we are going to have horizontal tangents, then it must come from the other subcondition, which is y equals 2x. Now, this I think is going to work. When you plug that back into the original, I'll do it up here. All right, it was y equals 2x, so what used to be x squared y will now be 2x cubed. Yes. Minus, and what used to be xy squared, when you square y, right, y squared is 4x squared. When you square the y and you multiply it by x, you get 4x cubed. 4x cubed equals 2. And fortunately, this looks like something that we can handle. Collect the like terms, let me just come down here. 2x cubed minus 4x cubed is minus 2x cubed equals 2. So then you divide by -2, you get x cubed equals -1. And so x must equal -1. Whew. Alright, so we found out. What did we do? We took the curve, found dy dx, set it equal to 0, got two sub-conditions. Alright, we got this and this. Now we found that this one didn't work in the original, but this one did. And under the condition, that led us to if this condition is to be satisfied, it means that x must equal -1. And if x equals -1, we plug that back into the condition, and we get y is, if x is -1, y is -2. So supposedly right now we have a horizontal tangent at -1, -2 on the graph. And I'll show you what it looks like later. We actually did get it right. But first I want to show that we can do these, we can do other things with these curves. We don't just have to set them equal to 0 or make them undefined. We can set them equal to anything we want, which is the next example. Suppose, alright, for the same curve, suppose that we were asked to find where the slope is equal to 1 instead. So not 0, not undefined, but 1. Well, what you get is this expression itself is the condition that has to be satisfied. Alright, when this is 0, then you can just basically ignore this unless it causes 0 over 0. But if it's something else, then you get a whole new situation on your hands. If dy dx is going to equal 1, then we can bring this term up and get y squared minus 2xy equals x squared minus 2xy. And lo and behold, the 2xy's, they cancel, and you get this subcondition from this, x squared equals y squared. Or another way to write this is that x equals plus or minus y. So this is the condition that we have to substitute back into the original. Alright, it came from the original thing, but like a simplified version of that is just, this is just a fancy way of saying x has to equal plus or minus y. So this is what we sub back into the original and see if we can make it happen. So let's first go with x, so I'll change the color. Let's go with x equals y. See if that is going to work. So when I substitute that in here, what used to be x squared y will now be x squared times x, which will be x cubed, minus, and what used to be x times y squared will now be x times x squared, will be x cubed, equals 2. And you can see that you get a false equation, 0 is 2. So once again, we find that if the condition is going to be satisfied in the original, it isn't going to come from x equaling y. It's going to have to be where x and y are opposite in sign. So this is what we're going to substitute back into the original now and see if we can make it work. So if x is minus y, then x squared is y squared, and so x squared times y will now be x squared times y is minus x, right, because they're opposite in sign. So x squared times y will be x squared times minus x, which will be minus x cubed, minus, and then what used to be y squared will now be x squared, so that'll be minus x cubed equals 2. And this is actually good news, because that's minus 2x cubed equals 2. And once again, we divide by -2. They don't all work this way, I promise. And you get x is right, x cubed is -1, so x is -1. And so that means if the condition is to be satisfied, it must mean that x is -1. And x is -1. That was gotten from the assumption that x and y were opposite in sign. So if x is -1, that must mean that y is +1, and supposedly this means that we have a tangent with a slope of 1 at the point -1, 1. And we do. I show you the graph. Here's the graph of that right here. I want to get that centered. Alright, the original thing that we started with, I found a horizontal tangent at the point, if you remember, -1, -2. So that's here. Alright, let me draw that in there. And here's the thing that we came up with for the with a slope of positive 1, that would be at -1, 1. And this one down here is the horizontal, alright, -1, -2. And if you try to set this, if you try to make this undefined, naturally you'll come up with this point here, and you should try that as an exercise. The answer that you get is 2, 1. But that's it. That's what you get when you when you're trying to find horizontals, verticals, or anything else that you could want.